Okay, the next topic that we are going to study is the concept of permutations. And first, we need to understand the definition of permutation. What is a permutation? A permutation is basically a rearrangement of the objects in a set into some sequence or order. So the shortest definition of permutation is ordering. Ordering is permutation. Permutation is not a number. When people ask the number of permutation, permutation means ordering. So we are basically asking the number of possible orderings. Now, in order to talk about a permutation, first we need to talk about a set of objects. So just like here, we have a set of objects. We have a black square, we have a white triangle, we have a white circle, and we have a black triangle. Now, a permutation of these objects is an ordering of these objects. So you see we have a possible ordering. We put the white circle into the first position, white triangle in the second position, the black triangle in the third position, and the black square in the fourth position. Now, the next one is another permutation. You see we have a set of objects, and a permutation is a rearrangement or an ordering of these objects. Now, how many different permutations we can create with distinguishable objects? So in the previous example, in this page, we have a set of objects, and all these objects were different from each other. So which means they are distinguishable from each other. Okay, we can separate these objects from each other. They are distinguishable. They are different. So if we have n different objects, how many permutations I can create? Okay, if I'm just going to put these objects in a linear order, how many different permutations or possible orderings I can create? In the first position of this permutation, I can choose to position any of these n objects. So there are n possible candidates to determine the first position. Now, once I position one of these n objects into the first position, to determine the object to be positioned in the second position, I will have n minus 1 remaining candidates because one of them is already positioned. So for the second position, I have n minus 1 different choices. Now, once I position the second object, for the third position, I will have n minus 2 remaining candidates, so on and so forth. Okay, so it is going to continue like this, and in the end, into the last position, I will only have one remaining object to position. Now, each of these positionings can be considered as an experiment. And by the generalized principle of counting that we have learned in the previous video, we can say that the number of different permutations I can create with these distinguishable objects is going to be n times n minus 1 times n minus 2 times so on and so forth, the multiplication of all these integers starting from n to 1, and that is called n factorial. So the number of different permutations I can create with n objects in a linear order is going to be n factorial, and that is due to the generalized principle of counting. Now, let us solve this question to understand the number of permutations concept. A statistics class consists of 6 men and 4 women. An examination is given and the students are ranked according to performance. So there are 10 students in this class. 6 of them are men and 4 of them are women. Everybody is ranked according to their performance, and we assume that no 2 students obtain the same score. So everybody is graded, but different students are getting different grades. The question is this: how many different rankings are possible? So in how many different ways I can rank these 10 students according to their grades? Now, each ranking corresponds to a particular ordered arrangement of 10 people. Therefore, each ranking is a permutation, and we have 10 factorial different permutations, which is 3,628,800 different permutations we can create with these 10 people. So that is 10 factorial. Now, for the second part, the question asks, if the men are ranked just among themselves and the women just among themselves, how many different rankings are possible? So the men are going to be ranked among themselves, and in a neighboring list, the women are going to be ranked among themselves. How many different rankings are possible? We have the first experiment here. The first experiment is ranking the men among themselves. And I know that there are 6 factorial possible rankings or 6 factorial possible permutations just among the men. And the second experiment is to rank the women among themselves, and there are 4 factorial possible rankings among these women, 4 factorial possible permutations. And because I have the first experiment to rank the men and the second experiment to rank the women, if I'm going to put these 2 lists next to each other, I will have a total number of different lists that I can create, or different rankings that I can create, equal to 6 factorial times 4 factorial by the basic principle of counting. So that is going to be 720 for 6 factorial times 24 for 4 factorial, and that is going to be 17,280 possible rankings I can create in this case. Now let's solve another questions related to the permutations of distinguishable objects. Miss Jones has 10 books that she is going to put on her bookshelf. Of these, 4 are mathematics books, 3 are chemistry books, 2 are history books, and 1 is a language book. So there are 10 books, 4 of them are mathematics books, 2 of them are chemistry books, 2 of them are history books, and 1 of them is a language book. Miss Jones wants to arrange her books so that all the books dealing with the same subject are together on the shelf. So there is a constraint here. Miss Jones is not going to just randomly order these books on the shelf. Her intention is what? Her intention is to put mathematics books close to each other as a group, chemistry books close to each other as a group, history books close to each other as a group, and because the language book is a single book, it is already grouped by itself. Okay, so there is this constraint. Actually, how many different arrangements we can create here is being asked, okay, under this constraint. Now, if there were no constraints, if Miss Jones was just randomly ordering these books on the shelf, then we would have 10 factorial different permutations of these books. However, we are going to arrange mathematics books with each other, chemistry books with each other, history books with each other first, then the book groups are going to be ordered among themselves as well. So first of all, we need to determine in which order we are going to locate these book groups on the shelf. Are we going to start with mathematics books or chemistry books or history books or a language book? So because of that reason, we need to say in the first place there are 4 factorial, or in other words, 24 possible orderings of the subjects on the shelf. Now, and for each subject ordering, the mathematics books can be arranged in 4 factorial different permutations among themselves, and chemistry books can be arranged in 3 factorial different permutations among themselves. History books can be arranged in 2 factorial different permutations among themselves. Finally, there is a language book. We are writing this 1 factorial here in any way, but 1 factorial is simply 1, so it does not affect this calculation. So by the generalized principle of counting here, I can multiply the 4 factorial permutations for the possible orderings among the book groups. 4 factorial here is the number of outcomes of the second experiment, which is the number of permutations among mathematics books. 3 factorial for the number of permutations amongst chemistry books, and 2 factorial for the number of permutations amongst history books. I multiply these factorial functions with each other by the generalized principle of counting, and that makes 6,912. So Miss Jones can arrange these books among the shelf in 6,912 possible orderings under the restriction that the same subject of books are next to each other. Now, how about we have indistinguishable objects? So let's just say we have several objects, but some of these objects are similar to each other. For example, I have 2 apples, 3 pears, and 4 plums. So I have these fruits. If I swap the position, if I create a permutation with these objects and swap the position of apples with each other, then the permutation that I'm going to create is not going to be a different permutation. It is actually going to be the same, because if I change the position of the apples, still I will get the same permutation. When you swap the position of these indistinguishable objects, you still get the same permutation. So this time, if we are going to count how many permutations do we have, we need to consider these swapping operations, and we need to consider the fact that we still would get same permutation if we make a swapping with the same type of objects. So let's try to understand the calculation. Suppose now there are n objects here. We have n objects. However, some of these objects are indistinguishable from each other. So we have at most r of these objects that are different from each other. We say that from the first type of objects we have n1 of them. From the second objects we have n2 of them. From the third type of the objects we have n3 of them, so on and so forth. Finally, from the last type, the r type of objects, we have nr of them. So basically we have n objects, n1 of them are of the first type. These n1 of them are indistinguishable from each other, or they are basically the same type of objects. There are n2 of the second type of objects, which are indistinguishable from each other. There are n3 of the third type of objects, so on and so forth. Finally, there are nr of the r type of objects. So the total number of objects is n. How many different permutations we can create with these objects, considering that swapping indistinguishable objects with each other is going to create the same permutation, is going to be calculated with this formulation, and we are going to explain why this formulation applies. Now, if these objects were distinguishable from each other, which means if all of them were different from each other, then the answer would just be n factorial, right? So we have already learned about this in our previous questions. However, you see, because we have n1 of these objects which are similar to each other, we divide this n factorial to n1 factorial. But not just to that, we are also dividing it to n2 factorial, because there are n2 objects which are similar to each other. So basically we are calculating the factorial functions of each number of same type of objects and divide the products, divide n factorial to the product of these. So this is how we calculate the number of different permutations of indistinguishable objects. So let us explain how this works. We have a chess tournament which has 10 competitors, of which 4 are Russian, 3 are from the United States, 2 are from the Great Britain, and 1 is from Brazil. So we have 10 competitors. If the tournament result lists just the nationalities of the players in the order in which they placed, how many outcomes are possible? Now, in the end of the tournament, if we were to see the names of the competitors, in that case, we would have 10 factorial possible rankings. However, the question tells us we will only see the nationalities in the ranking. Therefore, we wouldn't understand the difference between these Russian competitors, United States competitors, and Great Britain competitors if they are going to swap the positions of each other. So we say that if all of these competitors were different from each other, then we would say 10 factorial as the answer. However, if you create a different permutation among the Russian competitors, you will still get the same permutation. If you swap the position among the Russian competitors, you will still get the same permutations. Therefore, we need to count how many possible permutations we can create by swapping the positions of Russian competitors. So we can create 4 factorial different possible permutations by swapping the position of the Russian competitors. However, in the overall ranking, we will still see the same positioning. Therefore, we divide 10 factorial to 4 factorial permutations, which we can create by swapping the Russian competitors. Similarly, we need to divide it to 3 factorial for the United States competitors and 2 factorial for the Great Britain competitors. And we have 1 factorial here, which is ineffective again in the calculation. Therefore, the result is going to be 12,600. So there are 12,600 possible rankings we could have seen if the competitors are going to be ranked with respect to their nationalities. Now, how did we calculate this? 10 factorial is expanded, such as 10 times, 9 times, 8 times, 7 times, 6 times, 5 times, and we have 4 factorial as the remaining multipliers. Okay, so we do not have a full expansion here. We stop the expansion at 4, and after 4 we have just written 4 factorial. Now that 4 factorial here and the 4 factorial in the denominator will simply cancel out. We can cancel out 3 factorial 6 because it makes equal to 6. And we can cancel out 2 factorial with 8, and 8 becomes 4. Now you can simply multiply the remaining components in this multiplication, and that makes 12,600. Now let us solve another question to understand this concept better. How many different signals, each consisting of 11 flags hung in a line, can be made from a set of 5 white flags, 4 red flags, and 2 blue flags if all flags of the same color are identical? So we have 11 flags, but these flags are not totally different from each other. There are 5 white flags which are indistinguishable from each other. There are 4 red flags which are similar, and 2 blue flags again which are similar to each other. Now if I swap the position of the blue flags in a permutation, I would still get the same permutations. Therefore the answer is going to be 11 factorial for all possible permutations if the flags were distinguishable from each other. However, I'm going to divide this value to the number of possible permutations among each type of flags. 5 factorial for the white flags, 4 factorial for the red flags, and 2 factorial for the blue flags. Again, 11 factorial would be expanded as 11 to 6, 11 times 10 times 9 times 8 times 7 times 6 times 5 factorial. So 5 factorial can simply cancel out with the 5 factorial in the denominator. The remaining 4 factorial and 2 factorial can cancel out with the several components in the numerator, and we will only have the product of 11, 10, 9, and 7, and we can create 6,930 different permutations with these objects, some of which are indistinguishable from each other.